The essential elements that shape our physical reality, including the constants of nature, seem to be mere happenstance. In the bootstrap perspective, the universe emerges as a cohesive entity, suggesting that it is devoid of any fundamental randomness or chance occurrences. In this scenario, we can't simply scatter unintentional traits across various universes in a haphazard manner, much like the anthropic principle suggests. Until we uncover more solid and all-encompassing theories, we must recognize that the anthropic principle is just a stopgap for this conundrum. It exists in a captivating interplay between living beings and the cosmos, and while it may only be a preliminary framework, it still holds value until more compelling concepts emerge. When we encounter a wild organism, we are also greeted by the vast mysteries of our universe. Imagine a future where the arrival of an electron might also unveil the secrets of our universe. We will uncover the wonders hidden within a wild owl, an electron, or any other particle. In which corner of the cosmos is the cosmologist delving into the mysteries of that vast expanse? The physical universe unravels the secrets of how things operate, empowering us to shape our surroundings. However, it does not unravel the enigma of psychic phenomena, including the nature of consciousness and self-awareness. An individual who continually inquires about the location of life and consciousness within the physical realm will find themselves navigating through various scientific disciplines, akin to someone with an enigmatic ailment being shuffled from one expert to another. Biologists contend that life and consciousness emerge from complex physical systems made up of billions of organized cells, each a fascinating assembly of countless atoms. If this response doesn't quite hit the mark, the biologists might suggest a trip to the psychologists. Each psychologist offers a unique perspective. Some delve into the intricate workings of the mind, while others explore the complex neurological activities of the brain. Then, there are those who, acknowledging their limited understanding of the physical realm, suggest consulting physicists who are currently unraveling some fascinating mysteries. Some physicists might dismiss the matter entirely, claiming that if it isn't physical, it simply doesn't exist, while others may recommend consulting a biologist for further insight. In a moment of curiosity, the seeker may find themselves pondering the insights of the cosmologists. Some cosmologists admit they are completely in the dark when it comes to finding an answer. They understand, however, that universes emerge and vanish, birthed from the boundless creativity of the human imagination. They ponder if a creation of the intellect can truly unravel the complexities of the intellect itself. The ultimate question lies with the cosmologists, as they grapple with the enigma of containment. In which part of the universe is the cosmologist examining that very universe? Some scientists may sidestep the enigma by asserting it falls outside their realm of expertise. Yet cosmologists delve into the cosmos, and the enigma confronts them directly. Imagine an artist capturing the essence of his creative space on canvas. The artist resides within the studio, yet he refrains from illustrating himself engaged in the creation of the artwork. Exploring the act of painting reveals a captivating loop of endless images. A canvas captures the artist creating another canvas, which in turn depicts the artist at work again, spiraling into an infinite cycle of creation. The cosmos unfolds like a captivating canvas, with the cosmologist standing in a role akin to that of an artist, both seeking to unveil the mysteries that lie within. The cosmologist weaves a fascinating tapestry of existence, incorporating his physical form and brain, yet intriguingly omitting the very mind that shapes this captivating image. Imagine if he embraces the full spectrum of his consciousness, seeing himself as more than just a physical entity. In this scenario, he stumbles upon the delightful paradox of endless regression. The cosmos holds within it the cosmologist examining a cosmos, which itself houses yet another cosmologist probing a cosmos, and this curious loop continues on without end. Where, then, is the cosmologist delving into the mysteries of the universe? Is it possible for a picture to hold the essence of its maker? The physical universe, a tapestry of interconnected facts and ideas, intriguingly lacks the essence that molds those facts and weaves the ideas together. The puzzle of containment beckons to those caught in disagreement, challenging the notion that existence and consciousness are nothing more than a harmonious interplay of atoms. Typically, individuals who hold the view that existence and consciousness are entirely encapsulated by the physical realm frequently conflate it with the enigmatic universe, mistaking the facade for the essence. The enigma of containment weaves through every realm imaginable: the divine cosmos of theologians, the intricate psychocosmos explored by psychologists, and the tangible universe dissected by physicists. The solution to the containment enigma reveals that we, the architects of universes, dwell within the realm of the unknown. We, the creators of visuals, inhabit the cosmos. Our creations are the realms we frequently misinterpret as our reality. Every universe is a canvas, showcasing not just life and consciousness, but their physical manifestations, like vibrant wildflowers and intricate brains. The realm of existence encompasses both the body and the brain, yet it is not the force that holds this realm, which in turn includes the body and the brain. Gazing at the vast expanse of the starry universe invites a sense of wonder about its origins. Should we take a step back and allow the pieces to come together before seeking answers to this cosmic puzzle? Yet, if we had remained entirely rational and patient, it's likely that the wonders of science would never have emerged, and we might have settled for a mundane life, devoid of the thrill of discovery. In this fascinating exploration, the mind boldly seizes upon a solution long before it fully materializes, catching only the faintest hints of possibility. This instinctive grasp allows us to speculate on answers rather than simply bide our time. Henri Poincaré, French mathematician, 1913. The realm of the physical universe is made up solely of tangible entities, all intricately bound by the rules of nature. Could the law of natural selection be considered a fundamental principle of the universe? Since the era of Charles Darwin, numerous individuals have asserted that we cannot establish a connection between fossils of different forms through evolution and natural selection, a claim that seems to be based on mere conjecture. Yet the principle of natural selection is as tangible as the force of gravity. Natural selection hinges on three essential elements: a breeding population, genetic diversity within that population, and an environment that influences survival rates differently among its members. The variations that boost survival rise to prominence within the population, leading the species to transform and evolve as it persistently adjusts to an ever-shifting environment. Every day we encounter fascinating evidence that showcases the power of natural selection at work. The extensive application of antibiotics, like penicillin, has led to a fascinating twist in the tale of medicine, as it has inadvertently fueled the rise of more resilient strains of pathogenic bacteria through the process of natural selection. The challenges presented by time-like edges delve into realms that spark more philosophical contemplation than mere physical analysis. A universe shaped by the Big Bang possesses a distinct starting point, creating a fascinating boundary in the fabric of time. Should this universe revert to a Big Bang, it possesses two temporal boundaries, an origin and a conclusion. These cosmic boundaries are likely not abrupt, like cliffs in the Stoic universe, or solid like walls in the Aristotelian universe, but rather resemble the subtle fading of the medieval horizon. The physical world, with its structured timeline of events in cosmic time, might just unravel into a wild, chaotic dance at both its inception and conclusion. In reality, the enigma of time-like cosmic edges eludes our grasp, possibly due to our incomplete understanding of the very essence of time itself. Considering that time, much like space, is a tangible aspect of our universe, we can conclude that physical time exists solely within the confines of the physical universe and cannot reach beyond its boundaries. It's fascinating to consider that time may not have any meaning outside the boundaries of our universe. What could that imply about existence itself? Even with these comments, there exists a fascinating approach to discussing the events that unfolded prior to the dawn of our universe. Imagine a scenario where our universe serves as the birthplace of another physical realm, either emerging by chance or crafted intentionally by sentient beings in the original universe. In that light, we can delve into the events that unfolded in the parent universe prior to reproduction. Joe Rosen from the University of Central Arkansas has revealed a fascinating concept. The spring universe has the ability to replicate its parent universe, delving into the realms of self-generating universes and the many worlds theory. In this fascinating interplay, parent and offspring universes weave together a cosmic tapestry that is perpetually self-generating. Universe X gives rise to Universe Y in its own time, while Universe Y, in turn, brings Universe X into existence in its own unique timeline. The nature of creation varies significantly between what is contained and what is uncontained. The concept of contained creation refers to the fascinating moment when something that never existed before suddenly comes into being at a particular time and place in the universe. Consider the fascinating processes at play: the emergence and disappearance of particles, the blossoming of a flower, and the miraculous arrival of a child. The concept of uncontained creation alludes to the boundless and eternal emergence of the universe, inviting curiosity and wonder. When the topic of the universe's origins comes up, many envision a singular act of creation, which can skew their understanding. This leads to the intriguing question: what existed prior to the universe's inception? Thomas Huxley, 1825 to 1895, a renowned biologist and ardent supporter of Charles Darwin's theory of natural selection, penned a thought-provoking piece for the inaugural issue of the science journal Nature in 1869. He expressed, "It seemed to me that no more fitting preface could be put before a journal which aims to mirror the progress of that fashioning by nature of a picture of herself in the mind of man, which we call the progress of science." The journey towards a comprehensive cosmology will only truly commence with the emergence of a profound philosophy of mind. A philosophy of mind should captivate both the behaviorists, eager to transform the mind into something tangible for experimentation and precise measurement, and the idealists who yearn to understand the striking contrast between a mindless universe and one that is intricately woven into a vibrant, sentient whole through the essence of consciousness. Edwin Burt, The Metaphysical Foundations of Modern Physical Science. The realm of human sciences finds itself at a crossroads, as the very essence of the self they explore is rooted in the transcendental. G. Stent, Boundaries of Human Scientific Comprehension. At the heart of all understanding resides a captivating enigma, where the creator and the creation intertwine. The enigma of containment has lingered in philosophical discussions for ages, and now it casts its shadow over the realm of physics as well. Leon Rosenfeld, in Niels Bohr's contribution to epistemology, reveals how, during the formative years of quantum theory, Bohr found himself captivated by Paul Müller's The Tale of a Danish Student. The student finds themselves in a puzzling scenario within the realm of epistemology, where the nature of knowledge is questioned. Here, a man splits into two personas. One seeks to deceive the other, while a third, identical to the first two, observes this intriguing clash with a sense of awe. The quest to identify the true self feels like an endless riddle, where pausing at one persona only invites another to take its place, leaving me in a captivating loop of identity exploration. My mind spins in a delightful chaos, as if I were gazing into an endless abyss, and the conclusion of my thoughts leads to an excruciating ache. In Mind and Matter, Erwin Schrödinger observes, "Without being aware of it, we exclude the subject of cognition from the domain of nature that we endeavor to understand. We find ourselves retreating into the position of an observer, detached from the world, which through this very act transforms into an objective reality." Schrödinger elaborated, "A compelling understanding of this universe has only been achieved at the significant cost of removing ourselves from the equation, retreating into the position of an indifferent observer." Schrödinger then turned to religion. Can science vouchsafe information on matters of religion? Can the results of scientific research help foster a reasonable and satisfactory attitude towards these pressing questions that sometimes plague everyone? Some of us succeed in shoving them aside for long periods. Others, in advanced age, have satisfied themselves that there is no answer and have resigned themselves to giving up looking for one. While others again are haunted throughout their lives by this incongruity of our intellect, also haunted by serious fears raised by time-honored superstition. I primarily refer to the questions about the other world, life after death, and their associated aspects. In Men Like Gods, H.G. Wells introduced the idea of parallel universes, occupying what might be called superspace. Normally they remain isolated, but Wells and several more recent science fiction writers assert they occasionally make contact. Recent theoretical developments have also enlarged the notion of containment to embrace many universes as self-contained members of a superuniverse. Andrei Linde, a Russian physicist, treats the universe as an eternal, self-reproducing multiverse in which universes spontaneously generate new universes. Consider an ensemble of self-contained universes covering all possible values of the fundamental constants of physics. Suppose all these universes are virtual. They all exist in potential form, and each only becomes real by observation by conscious life. Because each is self-contained, the only possible observations are by internal forms of life. Thus, only those universes are real, and the fundamental constants are compatible with the existence of life. What happens in a universe like ours that passes through an early, lifeless stage? In the early stage, no conscious life exists to observe. Does it exist? Presumably, it evolves in a virtual state and becomes real through observation when conscious life exists. This seemingly weird picture of virtual potential versus real actual is common in the theory of quantum mechanics. A wave function consists of many evolving parallel virtual states, all of which are potential candidates for a real, observed state in the real world. The anthropic principle states that the universe is as it is because we exist. The theistic principle posits that it is because a supreme being created it for living creatures. According to the first principle, an extra-cosmic agent determines the cosmic design. According to the second principle, our existence determines the cosmic design. the two principles are not in direct conflict, and it may be argued that the first encompasses aspects of the second. Consider an excited atom in which an electron transitions from an initial state to several permissible states. The actual final state is unpredictable, but its probability is known. Hugh Everett proposed in 1957 that during such a transition, the universe splits into separate universes, each containing all permissible states. Thus, from each atom, many new universes are created each time. A transition occurs, and these universes are identical, except that in each one, the atom is in a different final state. A human being composed of many quantum transitions continually splits into numerous beings, occupying different universes, each in a slightly different state and following a different history. Could the solution to the dilemma of indeterminism be a universe in which all possible outcomes of an experiment occur? Why not apply this idea to the concept of free will? When a person must choose between two options, does the universe split into two or more universes to accommodate all choices? In this way, we resolve the conflict between free will and determinism. Rigid determinism operates in each separate universe, but a person enjoys complete free will by moving from universe to universe. All universes are virtual, except for the one the person occupies, which is the only real universe. We demand that our universes be rational and deterministic, even at the cost of creating a bizarre many worlds picture. My preferred view is that at each decision, the branching universes are virtual, except for the one that contains consciousness. Thus, free will reigns supreme, and determinism dwells in the shadows. Alternatively, free will belongs to the universe, and determinism, as conceived by the human mind, belongs to it. We do not know what consciousness is, except that it is not part of the physical universe. Gödel, in 1931, showed that mathematical systems are not fully self-contained. In a self-consistent logical system, free of internal contradictions, statements can be formulated whose truth is undecidable. When the system is enlarged with additional axioms, the previous statements of uncertain truth can be proved true. However, the enlarged system contains new, undecidable statements that can only be proved true by making the system larger. One conclusion is that the mathematician is inseparable from mathematics, just as the cosmologist is inseparable from cosmology. For a discussion of Gödel's ideas, see Gödel's Proof by Ernst Nagel and James Newman. What is the name of this book? By Raymond Smullyan. Scientists have answered some questions beyond reasonable doubt and have stitched these findings into a compelling, if not detailed, map and history of existence. John Horgan, The End of Science. Is a real theory of the physical world possible? It has been suggested that string theory offers the prospect of a final theory. String theory attempts to unify gravity and quantum mechanics so that subatomic particles consist of tiny strings with various vibration modes. In Dreams of a Final Theory, Steven Weinberg writes, "Our present theories are of limited validity, still tentative and incomplete. But behind them now and then we catch glimpses of an NL theory, one that would be of unlimited validity and entirely satisfying in its completeness and consistency." In contrast to the modern concept of a final theory, we may consider the medieval principle of learned ignorance. In his work On Learnt Ignorance, written in 1440, Cardinal Nicholas of Cusa argued that the more we know, the more aware we become of our ignorance. This form of enlightened ignorance he referred to as learned ignorance. The darkness of unlearnt ignorance disperses, and the brightness of learned ignorance grows with knowledge and wisdom. He wrote, "No man, even the most learned in his discipline, can progress farther along the road to perfection than the point where he is found most knowing in the very ignorance that characterizes him. And he will be the more learned, the more he comes to know himself as ignorant. One might dare to hazard that glimpses of a ANL theory have frequently occurred in history, particularly when the current universe was ripe for change. Consider the unlearned, unaware of their ignorance, who think they know everything. As knowledge increases, ignorance decreases. But this kind of ignorance, unlearned ignorance, is no more than a lack of knowledge. With knowledge comes awareness of the ignorance we have learned. And the more we know, the more aware we become of what we do not know. Edward Harrison, Masks of the Universe. From the heroic age of Greece until modern times, we see the development, side by side, of two views on the nature of space: dressed space and undressed space. Space as a void, undressed, existing in its own right, independent of the things it contains, was initially a lofty abstraction that many could not take seriously. It seemed more natural to think of space as dressed and made real, with a continuous covering of material and ethereal substances. Aristotle, who believed in dressed space, regarded the notion of a vacuum as nonsense, and said that a vacuum is nothing, and what is nothing does not exist. These beliefs enabled him to argue in favor of a night universe. The ether, the fifth element, ended at the sphere of fixed stars. Beyond the sphere of stars, there could be no space because there was no ether. Initially, this was the view of scholars in the Middle Ages, who later succeeded in extending space beyond the sphere of fixed stars by attributing it to God. It was also the view of René Descartes, and the Cartesians hold similar views, who extended space indefinitely by supposing it to be composed of tenuous and continuous matter. Numerous continental scientists and philosophers in the 18th and 19th centuries clung to the Cartesian view. But experiments with air pumps in the 17th century convinced many other scientists, particularly the Newtonians. The Cartesians resisted such evidence and argued that stored isolated specks of matter surrounded by voids cannot exist because space is illogical, and matter must always be continuous, however low in density. Matter exists everywhere, for if there were no matter, there could be no space. Aristotelian beliefs in modified forms persisted until the early 20th century. Even if space exists by itself, many think that space is still a sort of nothing, lacking substance and possessing only extension. Elegant equations of the electromagnetic field, with which James Clerk Maxwell unified electricity and magnetism in the 19th century, showed that waves of light travel at night speed. All electromagnetic waves, from radio to X-rays, travel in space at the universal speed of 300,000 kilometers per second. As we know, sound waves travel in the atmosphere, consisting of air undulations. How can waves of light in space consist of undulations of emptiness? In response, physicists labeled the universe with a subtle luminiferous ether, supporting light propagation and all other electromagnetic waves. The advent of special relativity helped to shake off the Aristotelian heritage, and nowadays we think in terms of the propagation of electromagnetic fields and see no need for an ether. An undressed space continuum that exists in its own right, absolute and independent of all contained things, is an abstract idea that originated with the ancient atomists. Accompanied by the idea that forces can act at a distance, it later became the master concept of the Newtonian universe. In the 20th century, undressed space developed into the space-time of special relativity. Then, with the rise of general relativity, space-time became, again, dressed with dynamic geometric curvature and the virtual states of the vacuum. the algebra connection, Descartes combined geometry and algebra into analytical geometry. He used coordinate systems in which the position of a point in three-dimensional space is specified by the values of the three coordinates, x, y, and z. Ancient Egyptians used two-dimensional grids or graphs for land surveys, while others in later ages used them for map making. Scholars at Merton College in Oxford also utilized them for calculations during the late Middle Ages. Space and time. Nothing puzzles me more than time and space, yet nothing troubles me less. Charles Lamb, in a letter, 1810, notes that scholars at Oxford and Paris in the 14th century made significant strides in clarifying our notions of space, time, and motion. They invented diagrams combining space and time in their studies of motion. Later, in the 17th century, the Cartesians and Newtonians established scientific pre-relativity concepts of space, time, and motion. Mathematicians in the 19th century studied the theoretical properties of multidimensional spaces, and Charles Hinton, in 1887, advanced the idea of time as a fourth dimension. Then came the relativity theories in the early 20th century that indissolubly combined space and time into a space-time continuum. We clearly understand space. It encompasses everything around us, extending outward and containing objects that are visibly distributed. Distance intervals span it, and we measure it directly with meter sticks in units, like meters. Time is not basic, because we cannot objectively observe bodies distributed in it, nor can we directly observe intervals of time with our senses, such as seconds. We seem to experience time intervals subjectively and cannot objectively observe them. The impression is that all our experiences can be categorized into two kinds: objective things, trees, clouds, and mountains, that are diverse in space, and subjective things, sensations, emotions, and ideas, that are diverse in time. Somehow these opposite experiences combine to form our phenomenal world and the physical world we theorize about. The nature of time is a perplexing subject that provokes endless philosophical discussion, and the words of St. Augustine of Hippo in the 5th century still strike a responsive chord. What then is time? If no one asks me, I know what it is. If I wish to explain what it is to him who asks me, I do not know. The time that we experience as human beings, the time that devours all things, according to Ovid's metaphor, is not quite the same as that used in science. Science simplifies the time we experience into a continuous one-dimensional space that conforms to the Hausdorff axioms. We should not be too surprised if physical time lacks some of the characteristics of the time we experience. Usually, we regard the neglected characteristics as psychological or metaphysical. The fourth dimension, physics, seizes time, strips away many of the characteristics ascribed to it in everyday life, and makes it akin to space. Our physical world has become a four-dimensional continuum that decomposes into a three-dimensional space and a one-dimensional time, stretching from the past to the future. The restless world is in a state of continual change. At any instant in time, there is one distribution of things in space. Then, at a later instant, there is another distribution. Hinton initiated a revolution in our understanding of the world around us when he demonstrated that its continual change can be tamed and made orderly by displaying it in a joint space-time diagram. Time has the properties of a one-dimensional space, said Hinton, and past, present, and future events form a continuous sequence in much the same way as the points of a straight line in space. Drawing three-dimensional figures on a two-dimensional sheet of paper can be a challenging task. Drawing four-dimensional figures on a sheet of paper, with time included as the fourth dimension, is even less easy. Some might say impossible. Frequently, in pre-relativity space and time and relative city space-time diagrams, only one of the three dimensions of space is shown. In his diagrams, Hinton used two dimensions of space, with time as an extra dimension perpendicular to space. In space and time diagrams, a point represents an event, such as the ash of a ray or the blink of an eyelid, and happens at a point in space at an instant in time. A line called a world line represents something that endures, such as a stone or an atom, and occupies a position in space at each successive instant in time. Of paramount importance is the fact that nothing changes in a space and space-time representation. Nothing ever happens. We have tamed the restless world by preserving it in a frozen state throughout space and time. We display everything as it was, as it is, and will remain in a world devoid of tension. A space and time diagram remains unchanged as the use of time only occurs once. The frozen four-dimensional world, in which time is one of the dimensions, was dubbed the block universe by the philosopher William James, who emphasized the complete absence of change in a space and time world. The four-dimensional world of space and time is fixed and unchanging. We must refer to all its regions in a common tense. In a tenseless world, it is wrong to say that an event has happened, another is happening, and yet another will happen, for all are present together. It is also wrong to say that a body moves along a world line from the past to the future, for the body exists at all segments along its world line. We must exercise caution and remember that the four-dimensional world already embodies time, rendering its use irreversible. If we make a mistake and say that a particle moves along its world line, we are confronted by the question of the speed at which it moves through time. This compels us to invoke a second time, and having admitted the possibility of movement through time, we must decide at what speed the particle moves through this second time. Motion through time opens up the prospect of serial time, consisting of an infinite regression of time-like dimensions. We avoid this absurdity by realizing that space-time has no physical changes. The arrows of time. World lines do not have arrows attached to them pointing in the direction of the future. In space-time pictures, it isn't easy to see what determines the past and the future. When a space-time picture is turned upside down, little or nothing in the picture prevents us from relabeling the new top as the future and the bottom as the past. The past and future are labels that often have no intrinsic meaning in the context of space-time. Yet, a time-reversed universe is completely different. Life begins in the cradle and ends in the grave. Cool objects grow hot. Candles and stars emit radiation, and everything is in a topsy-turvy state. Presumably, such time-reversed worlds lack life and are ruled out by the anthropic principle. Most of the fundamental laws of physics fail to distinguish between the past and the future and are said to be invariant in time reversal. The motion equations of bodies and many laws of microscopic physics are reversible in time. Their effect remains the same when the space-time picture is turned upside down and the labels for past and future are interchanged. Thus, two particles come together, interact, and move away. In the time-reversed picture, the same thing happens. Two particles again come together, interact, and move away from each other. Their motions and interactions are time-reversible if they can be displayed graphically. Like our space-time diagrams, our physics equations use a spatially defined form of time with no intrinsic direction. Even the equations that govern the propagation of light are time-reversible. According to experience, absorbed light originates from the past, and emitted light travels into the future. When the space-time picture is turned upside down and past and future are relabeled, light arrives from the future and departs for the past, contrary to experience. Electromagnetic theory does not forbid this bewildering situation, and nothing in the space-time picture says that light rays must propagate only into the future. Time has properties that, not only in life but also in the laboratory, cannot be entirely spatialized. The hour of heat. Thermodynamics is a branch of macroscopic physics devoted to studying all aspects of heat. The first law of thermodynamics deals with the conservation of thermal and other forms of energy in dynamic systems. The second law deals with the time reversibility of thermal systems. Strictly reversible systems are ideals that never exist, but enable us to perform simple calculations. Non-reversible systems are found in the real world, where heat is always lost at every stage of the process. Reversible systems have constant entropy. In the real world, entropy always increases, while energy, although always conserved, assumes less and less effective forms. The owner of heat from hot to cooler regions is not time reversible, because entropy would decrease. No scientist would dream of contradicting the second law of thermodynamics by saying that heat goes from cool to hot regions. A mug of coffee on my desk gets cooler in the direction of the future and hotter in the direction of the past, and in the process, entropy increases. Total energy remains the same, but it is less accessible, and this scenario is another way of saying that entropy has increased. If this did not happen, then you and I would not exist. The laws of thermodynamics that govern the mug of coffee and its environment are not time reversible. Yet, strange to say, the laws that govern the behavior of the individual particles that constitute the mug of coffee and its environment are time reversible. Heat continues to owe from hotter to cooler regions, when the direction of time is reversed in the equations that control individual particles' microscopic motions and behavior. It seems that the collective behavior of many particles acts as an arrow of time, whereas the behavior of individual particles lacks any arrow of time. Let us try to understand in an elementary way what happens in the space-time picture when heat flows from hot regions to cooler regions. We can regard heat, in this case, as an agitation of particles. The hotter the particles, the more agitated their motions. Agitated particles move about and have wavy or crinkled world lines, and crinkled world lines communicate their agitation by collisions and other interactions with neighboring and less agitated world lines. Hot or crinkled world lines, surrounded by cooler, less crinkled world lines, are cooler in the future direction. This is another way of stating the second law of thermodynamics. If shown a space and time diagram with many crinkled world lines, you immediately know the past and future. The agitation of isolated individual particles is unaffected by time reversal. Still, their collective behavior, the spread of agitation from hot world lines to cooler world lines, is governed by the second law of thermodynamics and is not time reversible. Single particles are time reversible, but systems of particles are not. It is like hanging a picture on a wall. If you look closely at individual dabs of paint, you will never know which way to hang the picture. You have to stand back and look at large areas of many dabs to determine the right way to hang the picture. The universe consists of numerous many-particle systems, for example, living creatures, planets, stars, and galaxies, and most scientists believe that the arrow of time is determined either partly or fully by the collectivist statistical behavior of these many-particle systems. Over time, the organized energies of these systems become disorganized and dispersed, and their states of order tend toward disorder. In trillions of years, when all stars have died and all systems have attained their lowest accessible energy levels, it will be difficult to determine the direction of time. In our universe, where matter is distributed irregularly in the form of stars and galaxies, we observe energy continually cascading into less accessible states of energy and are provided with a cosmic arrow of time. This raises the question, is there no arrow of time in a perfectly uniform universe, without irregularities? Such a universe might be expanding, and the change in its density will identify the past and the future. But how would we know that it is expanding? It may be contracting, and the higher density lies in the future, not the past. Thomas Gödel of Cornell University has argued that the universe gets its sense of time direction from its expansion, and the future always lies in the direction of diverging world lines. In this case, it is unclear what happens if the universe ceases to expand and begins to collapse. Our everyday experiences make us acutely aware of the now as a moment or segment of time. We, but not Aborigines, Mayans, Hopi, and many other societies. Imagine time as a river. Our boat, now, drifts on the river of time, gliding past a changing landscape, with the future always approaching and the past receding. Alternatively, we can think of the now as a wave of vividity that divides the known past from the unknown future. We are aware of transience, of things becoming, bursting forth into actuality, and then fading into a limbo of memory. Our awareness seems like an asymmetric wave of vividity advancing into the future, having an intensity that is almost zero ahead, rising sharply to a maximum at the present moment, and then falling slowly into the past. Our languages embody a mixture of primitive and sophisticated metaphors concerning the nature of time, and there. Contact leads to confusion and paradox. Amidst this confusion, we discuss being and becoming, free will versus determinism, and the arrow of time. So far, we have failed to harmonize the discordant concepts of temporal continuity, states of being, with transience, states of becoming. We only need to ask at what speed the now moves through time. At what speed does our boat drift on the river of time? To realize that we still do not understand time. Each of us in space-time is a world line, a bundle of interwoven world lines, like the fibers in a rope. This representation, however, does not explain the now that moves up the world line from the past to the future. Hermann Weyl, 1949, wrote, "The objective world is that it does not happen. Only to the gaze of my consciousness, crawling upward along the lifeline, world line of my body, does a section of the world come to life as a meeting image in space, which continually changes. A simple model of this process consists of a space-time diagram of world lines, over which a cardboard sheet with a horizontal slit is placed. The slit, which exposes a thin slice of space-time, reveals a three-dimensional world of space. The world lines passing through this space are particles occupying points in it. As the slit moves upward, we observe the particles moving through space. Fully spatializing time leaves us unable to physically explain our experience of transience in a constantly changing world. If the now moves upward along a world line, at what speed does it move? Must we invent a second time to account for this motion in time? If this second time is spatialized like the first, then we need a third time, and so on. We have the frightful prospect of serial time. If time is fully spatialized, we encounter the paradox of motion, regardless of the number of dimensions we assign to it. Transient scientists, confronted with how we move through time, tend to dismiss it as a metaphysical rather than a physical problem. Many are inclined to the view that it is a psychological illusion. However, such views never seem convincing and can be dismissed with Gerald Whitrow's words, How do we get the illusion of time's transience without presupposing transient time as its origin? The Natural Philosophy of Time, 1980. Whitrow also makes the perceptive comment that time is not itself a process in time. The physical time incorporated in space-time is a refinement of Newtonian time. And Newtonian time, which is still used in sciences apart from physics, is a refinement of colloquial time used in cultures of European origin. Many people believe that space-time incorporates real time, and that an awareness of transience is a non-physical peculiarity of living creatures. This view revives the Parmenidean doctrine, according to which the real world is changeless, and our transitory experiences are illusions. Which is the real thing, the idea or the experience? Opens the endless discussion. If ideas derive from experiences and experiences are illusory, how can ideas be more real than experiences? The real problem is, if living creatures are nothing but bundles of world-line burrs in space-time, how can world lines have an illusion of transformation when nothing in space-time changes? How can we hope to explain the illusion of transience without presupposing the existence of transience? We still do not know the answer to Whitrow's problem. We embark on journeys through the vastness of space. But what if we could also navigate the enigmatic realm of time? The concept of traversing time, woven into the fabric of storytelling, since ancient times, often unfolds through dreams, typically revisiting the past, as seen in Neville Shute's An Ancient Captivity, or through suspended animation, propelling us into the future, like in H.G. Wells's The Sleeper Awakes. The idea of a time machine, capable of whisking someone to different eras, first emerged in Wells's The Chronic Argonauts, 1888, and was further developed in The Time Machine, 1895. Influenced by Charles Hinton's theories, which suggest that time is akin to space and serves as a fourth dimension, Wells's imagination sparked a wave of science fiction, exploring the thrilling possibilities of physical time travel. Journeying into the past presents fascinating dilemmas about cause and effect. The happenings of yesteryear shape our current reality. If we venture back and change a pivotal moment, our return could unveil a dramatically altered world. Picture a reality devoid of time machines. Conversely, if we orchestrate a scenario where the time traveler's parents never cross paths, we conjure a universe that lacks the very existence of the time traveler. There's no need for concern. The concept of actual physical time travel, as depicted by Wells and various science fiction authors, is entirely and unattainable. This impossibility arises not from technical challenges but from a fundamental misunderstanding of space-time. In The Time Machine, the time traveler presents a miniature version of his grand time machine to a circle of friends who eagerly observe as he activates the model and propels it into the future. There was a breath of wind, and the lamp flame jumped. One of the candles on the mantel flickered and went out. At that moment, the little machine spun around, becoming a blur, almost resembling a spectre, for an instant, perhaps a swirl of shimmering brass and ivory, and then it disappeared. Aside from the lamp, what happened to the time machine? If it ventured into the future, it would remain on the table for 1 minute, 2 minutes, 1 hour, 2 hours, and so forth. Wells has missed the concept of a world line. He, along with other science fiction authors delving into time travel, tends to overlook two fundamental principles. In the realm of space-time, everything remains constant, with all world lines set in stone. Movement along a world line, as seen in the concept of now, delves into the metaphysical realm and eludes physical interpretation. Imagine a tale that bends the very fabric of reality, where the concept of moving through time collides with the fundamental rules of existence. Picture the essence of an object journeying through the ages. grappling with the paradox of vanishing into the past or leaping into the future. How does a tangible entity navigate this intricate dance, folding its narrative while traversing a universe that remains steadfastly unchanged? There's no need to fret about the idea of journeying back in time and causing paradoxes. We can only explore our world lines on a metaphysical level, with no possibility of changing anything. In 1949, the brilliant mathematician Kurt Gödel unveiled a fascinating solution within general relativity, revealing that world lines can indeed create closed loops under uniquely crafted circumstances. Journeying through the metaphysical realms of time allows one to traverse a world line into the future, ultimately leading back to the present by navigating through the past. It has been used as a popular literary device in numerous tales, where characters trapped in a time loop repeatedly experience the same sequence of events, as seen in the comedy film Groundhog Day. In all these tales, the trapped person remains fully aware of the cyclic repetition. Is this possible? A person's thoughts each time around the loop are repetitive. If the trapped person is unaware of the time loop in the first circuit, then they remain oblivious in the second and third circuits, due to the repeated identical events. Therefore, individuals trapped in their situation are often oblivious to their circumstances. In many instances, the trapped person alters the sequence of events and successfully escapes from the loop. How is this possible? Is this scenario possible when world lines never change? Is this possible when world lines never change? Philosopher-scientists in the 6th and 5th centuries BC identified two fundamental aspects of time: being, which refers to the Parmenidean continuity aspect, where time stretches from the past to the future, and becoming, which refers to the Heraclitean transience aspect, where everything is in constant change. These aspects remain unreconciled in both language and science today. Time flows endlessly from the past into the future, intertwining with the ever-changing nature of existence. This duality, often overlooked, leads us to ponder the age-old question: how does change occur within time? Back in the 5th century BC, Elea challenged the idea that our senses can truly grasp the essence of reality. He is best known for his paradoxes of motion, which attempt to prove that all apparent change in the sensible world is illusory. Only a few states of being exist. All states of becoming are an illusion, as illustrated by Zeno's paradoxes. Zeno's various paradoxes are similar, with the most well-known being the race between Achilles and the tortoise. In this scenario, the tortoise has a 100-meter head start, while Achilles runs at a speed that is 100 times faster than the tortoise. Achilles runs the 100 meters, and the tortoise moves 1 meter. While Achilles runs 1 meter, the tortoise moves 1 centimeter, and this pattern continues in infinite steps. Although Achilles always gets closer to the tortoise, according to Zeno, he never reaches or overtakes it. In this case, the paradox is usually solved by showing with infinitesimal calculus that the infinite number of steps occupies only a finite value of time, and Achilles is hence able to reach and overtake the tortoise, as observed by the senses. Many philosophers still debate Zeno's paradoxes. What is at issue is the assumption that time is continuous and infinitely divisible. Moses Maimonides, a 12th century Jewish scholar, delved into the concept of atomic time in the Guide for the Perplexed, referencing a solution to Zeno's paradox that was first introduced by the ancient Greek philosophers known as the atomists. This intriguing resolution breaks time down into infinite, indivisible atomic intervals, provoking thought and curiosity about the nature of reality. An hour is split into 60 minutes, each minute into 60 seconds, and each second into 60 parts, continuing this pattern until we reach elements of time that cannot be divided further, much like the concept of space. Thus, motion isn't a smooth flow, but a sequence of small jolts reminiscent of frames in a film, allowing Achilles to surpass the tortoise through these abrupt movements in the end. Maimonides, influenced by Aristotle and many Arab philosophers, challenged the views of the atomists. He proposed that the misty theory of time suggests the universe is created not just once, but repeatedly within each atomic interval. In the 10th and 11th centuries, Al-Kalam, a radical group of Arab theologians, rejected the Aristotelian foundations that supported mainstream Muslim theology. The Mutakallimun, the scholars of Kalam, drew upon the atomic theory of the Epicureans from the Greco-Roman era to illustrate that the universe is entirely contingent on the will of the supreme being, the singular force. Atoms are mere voids that create separation, with the sole agent, Bilan, orchestrating their arrangements. Ibn-Basra, who resided in Baghdad until he died in 1013, proposed that time itself is atomic. Within each atom of time, the sole agent reimagines the world in subtly varied forms. The world's creation is not a singular event, but a series of fascinating occurrences. The Ka theory insists on a singular agent for all explanations, dismissing any role of the natural world. It suggests that no forces animate the lifeless material realm. Yet, the Kalam theory intriguingly bridges the complexities of time. In every fleeting moment or atom of time, the material world unfolds in space, while memories of the past and hopes for the future extend through time. Existence seems to settle into a state of stasis. This state transforms, giving rise to a new static existence in a fresh atom of time. Fleeting moments of change can reshape entire static realities. When stripped of its more extreme theological implications, the Kalam cosmological argument offers a compelling perspective on our intricate experience of time. The Kalam atomic theory of time brings together the diverse characteristics of time in a fascinating way. This suggests the need for a fresh perspective on time, where the dual aspects of existence and transformation hold equal significance. It's essential to recognize that the journey of physics involves reshaping and letting go of previous notions that were once considered truths. Many in the scientific community are acutely aware of the transient nature of theories, often feeling a sense of discomfort when philosophers, biologists, and psychologists delve into the essence of time within the physical realm. Should we redefine the nature of physical time to embrace its dual aspects? The implications for the physical universe and cosmology could be profound. If the fundamental components are out of balance, we can expect remarkable shifts in our understanding of the cosmos. Here are some excerpts from the opening chapter of Wells's The Time Machine, where the time traveler shares his insights on the possibility of time travel with his companions. He describes 4 dimensions, 3 that we recognize as the planes of space, and a 4th that we call time. Interestingly, there appears to be an artificial separation between the first 3 dimensions and the last, primarily because our awareness flows in a single direction, through time, from the beginning to the end of our existence. I have been exploring the fascinating realm of 4-dimensional geometry for some time now. Some of my findings are quite captivating. For example, I have created a series of portraits depicting a man at various ages, 8, 15, 17, 23, and so forth. Each of these images serves as a 3-dimensional slice of his 4-dimensional existence, which remains constant and unchanging. Our mental experiences, which are intangible and lack physical dimensions, traverse the temporal dimension. Before you know it, Wells's narrative of time travel subtly shifts from the realm of the abstract to the tangible, transitioning from what seems possible to what stretches the imagination. The time traveler is determined to convince his friends of the possibility of time travel. In his hand, he held a shimmering metallic structure, not much bigger than a small clock, crafted with exquisite precision. "This little device," he explained, leaning forward with his elbows on the table and his hands clasped above the contraption, "is merely a model. It represents my design for a machine that can traverse time. Now, please pay close attention. This lever, when pushed, propels the machine forward into the future, while the other reverses its course. This saddle signifies the seat for a time traveler. I will activate it, and the machine will launch. It will vanish, journey into the future, and then disappear." And indeed, as he pushed the lever, the machine vanished into the future. In just a page or two, Wells transitions from the realm of metaphysical time travel, where no physical laws are broken, to the realm of physical time travel, which challenges the very foundations of causality and the concept of timeless space-time. In the realm of metaphysical time travel, the mind journeys along a world line, while, in the physical aspect, an object traverses its world line, carrying it along for the ride. The timeless discussion about the nature of free will invites a captivating exploration that sparks curiosity and wonder. People often find themselves convinced that they possess a certain level of control over their existence, believing they can shape the unfolding events around them at their discretion. However, if they exist within the confines of the universe, they must adhere to unyielding laws, rendering their perception of free will merely a captivating illusion. We find ourselves at a crossroads. Are we mere puppets, devoid of agency and accountability for our choices? Or do we possess a genuine freedom that eludes our current understanding and rational exploration? This argument applies not only to the physical universe, but also to all rational universes. Whether we embrace a rational spiritual dimension or not, we find ourselves entangled in the captivating puzzle of free will amidst the chaos of an indeterministic universe, or the absence of it in a deterministic one. Augustine of Hippo, a fascinating figure in the realm of Christian thought, championed the concept of predestination, distinguishing it from mere fate. There are just two paths to consider. One can embrace determinism and see free will as nothing more than a trick of the mind, or one can delve into mysticism, viewing the quest for natural laws as an exercise in futility. If it's essential, then it can't be deemed a sin. If it's merely a choice, it can certainly be sidestepped. Pelagius, a British theologian, existed during the era of St. Augustine. He found himself at odds with the concept of Augustinian predestination, as it appeared to absolve wrongdoing. The debate surrounding the notion of free will and personal accountability, which challenged the idea of divine omnipotence, sparked outrage among Christian leaders and ultimately led to the label of Pelagian heresy. Pelagius found himself compelled to escape the unfriendly shadows cast by Rome. In exploring the concept of fatalism, Michael Dummett presents a thought-provoking scenario in Causal Loops that draws on the London bombings during World War II too. He illustrates the fatalist argument by suggesting that if your name is inscribed on a bomb, your fate is sealed, regardless of any precautions you might take. Conversely, if your name is not on that bomb, you will escape unharmed, no matter how careless you are. This leads to a fascinating conclusion. In the first scenario, all precautions are in vain, while in the second, they become unnecessary. Thus, the essence of this perspective suggests that if an event is destined to happen, any efforts to influence it become irrelevant, and attempts to avert it are ultimately in vain. If it's not destined to happen, then any effort to make it so will be in vain, and attempts to stop it are unnecessary. Can a belief in fate carry us through challenging times? During my time as a student at London University, the bombing of London in World War II left a lasting impression on me. So, does it lessen motivation during peacetime? Every culture and every era crafts its narrative. The past is endlessly shapeable, constantly at the mercy of individual and collective egos. Twists and turns create the fascinating tales we refer to as history. Is it possible for history to transcend our desires and the interpretations of historians? The realms of Newtonian space and time were like communal gatherings, where all observers mingled and shared a collective experience. The gaps of space and the periods that divide events were unyielding. They were identical for all. In an enchanting apple orchard, a curious observer witnesses an apple tumble from its branch, descending 5 meters in just a fleeting second. Imagine a scenario where an observer, moving around a tree, witnesses it descends 5 meters in just 1 second, regardless of their movement speed. Intriguing. Now everything has taken a turn. The old Newtonian universe, with its ideas on the fixity of space and time intervals, is no longer the universe we inhabit. In the Middle Ages, intriguing diagrams of space and time showcased events and world lines, revealing a captivating complexity that isn't as daunting as it may seem. Up until the dawn of this century, they served as a stunning visual tool for illustrating the dynamics of movement. Then came the theory of special relativity, and diagrams of this kind acquired a new physical meaning. Towards the end of the 19th century, Albert Einstein's genius gave the theory of special relativity its final form in 1905. Today, physicists use it daily, having withstood innumerable tests. However, upon reflection, the theory remains as astounding as it was when it was first proposed. We must relinquish the notion that everyone experiences time and space at the same intervals by relativity. 2 new invariants are exchanged for these 2 old ones. The speed of light in space, represented by c, is the first of the new invariants. Regardless of the observer's motion, the speed, 300,000 kilometers per second, is the same for everyone and everywhere. In 1887, Albert Michelson and Edward Morley discovered that light travels at the same speed in every direction on the Earth's surface. This was a surprising outcome. The measured speed of light should be c to v in opposite directions, parallel to the Earth's orbital motion, which is 30 kilometers per second. This is what Michelson and Morley expected to find. Instead, they found that light moves in both directions at the same speed. As is well known, the Sun circles the galaxy's center at a speed of 300 kilometers per second. The local group of galaxies is where the galaxy itself moves, and the local group moves within the local supercluster. The speed of light remains constant in all directions, regardless of these motions. The speed of light about the particles is always c, even in high-energy experiments where the particle speeds are high. It is not surprising that light travels at the speed of light, which is the speed limit for all high-energy particles. Even for observers traveling at high speeds in opposite directions, the constancy of CE astounds them. For example, a body passes us at half the speed of light, and light travels at the same speed as that body around us. Light travels at 300,000 kilometers per second, a constant speed regardless of whether the body moves at 0.9, 0.99, 0.999, or 0.9999 degrees of separation. According to 19th century physicists, space is an empty void that cannot carry electromagnetic radiation, including light, unless it is filled with a substance known as luminiferous ether. Light waves moving through the ether resembled sound waves moving through the atmosphere. The observer's velocity in the air determines the perceived speed of sound. It is even feasible to travel faster than sound waves. The luminiferous ether's refusal to behave like air or any other medium was perplexing. The groundbreaking realization that space is more than just emptiness, and that light waves are more than just the undulations of an etheric medium, came about as a result of the discovery that the speed of light is invariant. Light waves evolved into a complex fusion of electromagnetic fields, where time and space combined to form a complex physical structure. Since space has its reality that makes the speed of light independent of relative motion, we no longer need to attribute physical reality to it by attributing an ether. The space-time interval is the second invariant. By themselves, time and space intervals are no longer invariant for every observer. Instead, they combine to create an invariant space-time interval. Keep in mind that we compute the distance in light seconds or years, when measuring time in seconds or years. The first invariant states that the speed of light is universal, so that we can measure space in terms of time units. The value of the space-time intervals between events is agreed upon by all observers, regardless of their relative motion. A unified four-dimensional space-time continuum is created by fusing space and time. The only public domain is space-time. Observers in relative motion have their private times and spaces. Hermann Minkowski's 1908 statement, "Henceforth, space and time are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality," emphasized this new understanding of the physical world. The invariance of periods in time and the invariance of distances in space are two outdated concepts that have been replaced. We have two new concepts in place of the invariance of periods in time and space: the invariance of the space-time interval and the invariance of the speed of light. Only space-time is now regarded as absolute, whereas space and time were once thought to be absolute entities. Instead, they are now viewed as decoupled dimensions from each observer's perspective. Minkowski's former pupil, Albert Einstein, 1879 to 1955, created the theory of special relativity and the associated algebra. Minkowski proved in 1908 that time and space diagrams are real representations of a four-dimensional physical reality rather than just handy mathematical constructs. Time and space, not just space, make up the universe. Three fundamental components make up space-time: null geodesics, light rays, lines, world lines, and points, events. Events represented by points in space-time diagrams are called brief happenings. World lines that stretch from the past to the future are things that endure, like observers. Light signals from the past are received by an observer, who then sends out signals into the future. These light signals travel 1 light second every second as they enter and exit the observer's light cone. There is a backwards light cone at every point in space-time. 300,000 kilometers is equivalent to 1 light second. The forward light cone extends forward in time and out into space, while the backward light cone extends backwards in time and out into space. Regardless of the inclination of the world line, the light cones of each observer at each world line point are similar. At speeds below or equal to the speed of light, all information is observable. Sound waves, for example, transmit information at a much slower rate than light waves. The events that have been observed must, therefore, be on or inside the backward light cone. The observer-influenced events must be located on or within the forward light cone. They disagree on the ordering of past and future events outside their light cone. Still, observers in relative motion at the same point in space-time always claim that events inside or on their forward light belong to the future, and events, according to the New York Times, one space-time observer in relative motion has a world line that is angled in the direction of another. As a result, the inclined world lines of observers A for Albert and B for Bertha indicate relative motion. They have distinct locations and times within space-time, rather than a shared space and time. Observation's space is a peripheral part of his world line, and he measures time along it. His time intervals are space-time intervals along his world line. Likewise, observer B's space is perpendicular to her world line, and she measures time along it. While B's space is perpendicular to hers, A's space is perpendicular to his world line. Regretfully, a single diagram is all we can use to demonstrate that space is perpendicular to one world line. This is due to the absence of space-time geometry on the paper sheets used to draw our diagrams. The fact that space-time geometry differs from our well-known Euclidean geometry of space and time causes considerable misunderstanding regarding exceptional relativity. Whereas A's time and space add to space's time, B's time and space add to space-time. Contributions from each other's times and spaces make up their spaces. The simultaneous occurrence of two distinct events in A's space does not happen at the exact location in B's space. Space-time does not properly decompose into space-time. The rule states that space decompositions into time and space are equally legitimate and authentic. That's why it's called relativity. The rules are straightforward. All observers experience the speed of light at the same speed, and all observers experience all space-time intervals at the same speed. Space-time, world lines, and light rays make up the four-dimensional world of space-time. Every event has a corresponding light cone, and every world line has a corresponding space. This is the theory of special relativity, and many elementary physics books contain the algebraic details, often without Minkowski's insight. The speed of light and space-time intervals are examples of quantitative laws that are invariant for all observers. In contrast, equations that are covariant for all observers, regardless of their relative motion, are regarded as covariant. Simple instances of invariance and covariance can be found in the Newtonian universe. The space and space intervals are invariant, meaning they are the same for everyone. When we toss a coin while flying in an aeroplane or on a ship at sea, it returns to our hands, precisely as if we were standing on the ground. Both on the ground and in the plane, the coin moves according to the same laws, which are unaffected by relative uniform motion. Since there is no inertial force acting on the observer, motion at a constant velocity is referred to as inertial. Exists. In a car moving at a steady speed, a passenger who has their eyes closed cannot tell how fast the car is moving. Vehicle speed. The motion is inertial. The passenger can only feel inertial forces and realize that the velocity is changing when the speed rises or falls, or the driver steers to the left or right. All accelerations are absolute, and all velocities are relative in a Newtonian universe. The laws of nature are covariant in a broad sense, according to special relativity. Imagine a laboratory without windows that is free to move and travels at a steady speed. It is an inertial motion. Regardless of the laboratory's velocity, the same outcome is always obtained when measuring the speed of light or conducting any experiment here. There isn't an experiment that can tell us the laboratory's velocity. The covariance of the laws of nature also holds for observers traveling at a constant speed in any laboratory. According to special relativity, if the observer's velocity remains constant, the motion is inertial, then the laws of nature are covariant. We are not too far from Newtonian concepts, even though space-time has a physical structure, where the space-time limit is the same for everyone. Acceleration is absolute, whereas velocity is relative. An inertial force, which is unique to the observer and not shared by other observers of different motions, is experienced by an accelerated observer. Similar to the Newtonian universe, the laws of nature in special relativity do not apply to accelerated observers, except for a particular class of objects whose motion is inertial, i.e. of constant velocity. The laws of general relativity are covariant for the broader class of observers in free fall, as we will see in the upcoming chapter. Physicists frequently use special relativity to analyze accelerated, non-inertial motion, despite the constraint of constant velocity. The triangle comes from Newtonian mechanics and is basic. CK originates from Newtonian mechanics and is straightforward. Let's say we are in a fast-paced laboratory environment. We obtain experimental results that are not strictly consistent with our covariant equation predictions. We don't give up in despair and discard the results. Remember that because of the Earth's rotation and revolution around the Sun, a laboratory on the Earth's surface is in non-inertial motion. Instead, we study the events in the accelerated laboratory while imagining ourselves moving inertially at constant velocity. We get the actual results and the necessary corrections for the observations made in the moving laboratory from the Cova laws that apply in our hypothetical steady state. This imagined steady motion is a constant tool used by physicists to comprehend and correct the outcomes of moving situations. To understand and rectify the outcomes of accelerated motion, STS continuously employs the concept of imaginary inertial motion. The shortest path between two events is typically not a straight line, and the geometry of space-time differs from that of a sheet of paper. Speeds near the speed of light. When bodies have relative speeds near the speed of light, space-time exhibits interesting properties. The majority of people find these findings unexpected and inexplicable. How is it possible for a space traveler to visit a galaxy millions of light years away in a typical lifetime? After returning to Earth, a space traveler discovers that his twin sister has aged, while he has remained the same age. The answer is straightforward and stems from the fact that space-time's geometry differs from that of the blackboard and the paper sheets we use to draw diagrams of space-time. The fundamental fact that distances between points in space-time are not space-time-like distances between points on a piece of paper is the root cause of all the misunderstandings surrounding special relativity. We are used to thinking that the shortest path between 2 points is a straight line. That is not true in space-time, but it is true in regular space. Let's look at light cones, or the routes that light rays take, to see why this is the case. Light travels through space in 1 light second. This indicates that the time interval for a light beam is equivalent to 1/4 of the space interval. On light, 2 events are always 0. Think about a star that is 1,000 light years away. This star's light travels at a tremendous speed across a vast expanse of space before entering our eyes 1,000 years later. There is no denying that light has traveled over great distances and a very long period. However, there is no space-time separation between the star and the eye. All events that send us signals have space-time distances of 0 along the backward light, and all events that receive our signals have space-time distances of 0 along the forward light cones. Despite its strange appearance, this explains why the speed of light is constant and forms the upper bound of all motion in matter. Think of a straight line that connects. A and B are 2 events. Additionally, consider the alternative path ACB, which creates the light cones that intersect at points A and B, i.e. A to C, and then C to B. When depicted on paper, each is longer than a straight line. However, space-time is zero in space-time. A straight line passing through A and B is the longest space-time distance between A and B. All other paths between A and B that bend towards the light cones are shorter. The so-called twin paradox arises from the inconsistency between space-time and common sense. A body's age is determined by the length of its world line from the beginning, and time is measured along this line. However, space-time straight world lines are those that connect any 2 points in space-time, even if they are bent or curved. As a result, someone traveling from point A to point B via a bent world line, like ADB, gets there sooner than someone traveling in a straight line. Both individuals use wristwatches or other physical methods, like counting heartbeats, to measure time, and the amount of time that has passed in each instance is equal to the world line's length in space-time. In space-time, twins are born together, and their world lines start at the same time. However, for the remainder of their lives, their world lines will travel in different directions, and their ages, as determined by the clocks they carry, will differ slightly whenever they cross paths. The world line is more crinkled because A spends his entire life at home, while B takes many plane trips. She has lived a somewhat shorter life and has a slightly shorter world line than him, according to a reunion honoring their 80th birthday. In this instance, the age difference is minuscule, possibly as little as 100 microseconds. It eventually makes its way back to Earth at a very high speed. The twins A and B were the same age before the trip, but it becomes clear right away that A is older than B after B returns. "You've cheated. You have gained time and I have lost time," says A. "No, I haven't," says B. "I am younger than you. My heart has beaten fewer times than yours. You have brushed your teeth more times and read more books than I have." Although twin B, who is traveling in space, goes through periods of acceleration and deceleration, the twins' asymmetric aging cannot be caused by acceleration alone. The age difference between A and B is larger if B travels a second, more extended trip at the same speed as the first one, and experiences comparable acceleration periods. Traveling close to the light cones causes twin B to age less. The farther she travels, the older she is when she returns. Now A can be seen moving away from the light. This must demonstrate that A should be younger than B, right? However, B must begin moving towards A at half-time, in B's time, and move closer to the light, increasing speed to catch up with A. Ultimately, light makes B appear younger than A, either A's space and time or B's. Space and time have the same computed age difference. Space travel at near light speed presents formidable technical challenges that will take time to resolve. For many centuries to come, humans are unlikely to encounter the strange phenomenon of asymmetric aging in any meaningful way. On the other hand, high-energy particles frequently experience asymmetric aging. The intrinsic lifetime of the muon, a subatomic particle, is measured along its world line. It decays into other particles in a millionth of a second. A muon travels far more than 300 meters before decaying when it moves relativistically or near the speed of light. It decays in a millionth of a second in its own time, measured along its world line, but it appears to decay much more slowly to those of us not traveling with it. This limerick could be accurate if it were to travel faster than light. At any time in the past or the future, we could set out on an interstellar voyage and return to Earth. Current theory, however, states that nothing physical can move faster than light. If it were possible to communicate faster than light, we could do impossible things. such as sending information back in time to alter the present. Alternatively, if it were possible to travel faster than light, we could do impossible things, such as stopping our parents from meeting. Fortunately for us, Wellesian time travel is not feasible. But this is bad news for science fiction authors. Let's consider the extreme scenario and assume that M-rays, M for mystic, travel at infinite speed to simplify the argument. M-rays are used for communication between people on Earth and a planet in another solar system. In Earth space, the farthest planet is located at a distance of L. In Earth space and time, signals from Earth at time t equals 0 travel instantly. The return signals reach the Earth in the past after traveling instantaneously in the planet's time. Signals from 10 years ago could be sent. Space-time travelers could visit Earth in the past by traveling at an infinite speed. Since the laws of physics forbid traveling faster than light, causality is maintained, and the impossible is avoided. Observe that the twin paradox prevents one from traveling into the past when traveling close to the speed of light. At instant Q, signals sent from Earth at instant P reach the planet instantly in Earth time, and they return instantly as well. The planet is seen moving away from Earth in B. The return signals travel instantaneously in the planet's time, arriving on Earth at instant R, which is in the past, while the signals sent from Earth at instant P reach the planet at instant Q. At instant P, signals are sent from Earth, travel at an infinite speed, and get to the planet at instant Q. The return signals arrive on Earth at instant R, which is in the future, after traveling instantaneously in the planet's time. If there were M-rays, we could use remote mirrors that move towards and away from the Earth to speak directly with our ancestors and descendants. Stars are bright, globular spheres of gas where pressure pushes outward and gravity pulls inward. The chemistry of planetary life is maintained by the low-temperature radiation from the surface that results from the release of nuclear energy at high temperatures in the interior. But there is a day of reckoning for every star. The star begins to die as its hydrogen reserves in the core are depleted. The star turns into a red giant when its outer regions swell due to the constant pull of gravity, causing the central areas to contract higher densities and temperatures. The majority of the matter in a star like the Sun is compressed into a sphere about the size of Earth when it transforms into a white dwarf. Many stars eventually become white dwarfs, which cool gradually and are supported internally by the pressure of electron degeneracy, much like regular metals. More massive with ease. These stars can utilize their remaining nuclear energy reserves due to their stronger gravity and central regions, which are still contracting to even higher densities and temperatures. These stars grow into bright giants that waste energy at an incredible rate. Their atomic energy stores are soon depleted. All that's left is gravitational energy, which comes at a deadly cost, constant contraction. These stars become blazing supernovas for a brief ecstatic moment as their cores rush inward and their mantles explode outward in their final throes. Neutron stars in the form of fast-rotating pulsars are born from these apocalypses. No known state of matter can stop the imploding cores of the most massive stars. When gravity, which is typically the weakest force, overcomes all resistance, a black hole is created. The core of a massive star reaches nearly infinite density if we fall with it in tens of microseconds after its last moments. It evolves into a singularity comparable to the very early universe, about which we still know very little. Perhaps the fundamental quanta of space-time are the only particles that survive these harsh conditions. An orderly, time-like sequence of events disappears in space-time, which is a dense foam where space and time are inextricably jumbled together. However, the falling star never reaches the singular state from the outside world. The star appears to fall more slowly as the gravitational redshift increases steadily. The redshift gets closer to infinity as the star gets closer to a critical size, called the Schwarzschild radius. The star turns red, rapidly turns black, and remains in the vital size indefinitely, trapped in a perpetual state of freefall collapse. According to classical theory, nothing can now escape to the outside world, not even light. Doom is just a split second away within the collapsing star itself. However, from a distance, the star appears to be a black hole where time is suspended, and the outcome of gravitational collapse remains unknown. Let observer B be far away in the outside world, and observer A fall into a black hole. "Why should I worry about A's fate?" asks B. "But is it true that A will never reach the singularity in my space and time, and will always be suspended in a frozen state?" According to theory, there is only one future singularity in a closed universe with normal pressure and density. The outside world appears blue-shifted to the observer inside the collapsing star, and this blue shift reaches its maximum value when the star reaches the Schwarzschild radius, or critical size, and turns into a black hole. As the collapse continues, observer A sees everything outside of it speeding up, becoming increasingly rapid. At the critical size, he notices that everything outside occurs extremely quickly. The universe's future history ends in a flurry. Please assume that the universe stops expanding and collapses back into a second Big Bang in the far future, which would be tens or hundreds of billions of years in our time, B's time. The outside world soars in density until it reaches the black hole's density, and the galaxies streak away and then back again, all of which are visible to the inside observer A in little to no time. Now, A and B, holding hands, descend into a cosmic singularity as time inside the black hole and time outside the black hole tick away at the same rate. After congratulating herself on avoiding the black hole, observer B outside finds herself on an equal footing with observer A inside, and the two of them meet their demise together. Binary systems. The majority of massive stars belong to binary systems, and we observed that the exchange of matter between stars complicates stellar evolution in close binary systems. In a close binary system, matter is spilt onto companion star Y when star X swells into a red giant. X then transforms into a neutron star or possibly a black hole due to its decreased mass. The collapsed star X gains mass, and if it is a neutron star, may implode and turn into a black hole as a result of the companion. Star Y swelling up and returning matter to it. After further development, the companion star Y eventually collapses into a black hole or a neutron star. It is hard to avoid the conclusion that many stars, whether isolated or in binary systems, have turned into black holes because the most massive stars have masses of 50 times or more than the Sun. Astronomers are interested in collapsed stars in binary systems. Companion star gas that falls onto a black hole or neutron star is heated and emits a significant amount of energy in the form of X-rays. There are many known binary systems of X-ray sources, where one of the companions is either a black hole or a neutron star. Typically, neutron stars have masses of less than 3 solar masses, and collapsed stars with higher masses are most likely to form black holes. The collapsed star in Cygnus X1, an X-ray binary source, is a candidate for a black hole. With a mass roughly 8 times that of the Sun, the collapsed star was, according to Newtonian theory, a significant event occurs when the escape speed from a body's surface equals the speed of light, as John Michell and Pierre-Simon Laplace demonstrated in the late 18th century. General relativity states that matter curves space-time, and curvature is a measurement of gravity's strength. A fixed mass body's surface gravity rises, and space-time becomes more curved when it contracts. The Schwarzschild radius is the critical size at which space-time becomes so curved that the body is effectively completely encased in it. Nothing can leave the body or the outside world, not even light, as it has become a black hole encased in curved space-time. We can better visualize the situation by using a stretched horizontal rubber sheet. We visualize a ball gradually getting smaller. We observe how the rubber sheet becomes more curved and depressed in the middle as we watch the ball on it shrink. Except for a thin connecting neck, the sheet eventually encloses the imaginary ball when it is tiny and dense. Because of the neck that connects it to the rest of the sheet, the ball is not isolated. Similarly, a black hole is not isolated because it is connected to the outside world. The mass of the ball determines the amount of depression in the sheet at a fixed distance from it. As a result, the curvature of the sheet does not change as the ball shrinks. In general relativity, this effect is comparable. When a spherical body of fixed mass contracts, the gravitational field, or curvature of space, stays constant at a fixed distance. No gravitational disturbances move away from a collapsing spherical body because space's curvature stays constant. A black hole's Schwarzschild radius is roughly equal to the mass of the Earth, or 1 centimeter. Both would turn into black holes with infinite redshifts if the Earth were to collapse into a sphere just smaller than a table tennis ball, or the Sun were to collapse into a sphere with a radius of 3 kilometers. Redshift. Two effects of light rays emanating from a luminous gravitating body are redshift and deflection. Light rays emitted from a spherical body of fixed mass are increasingly redshifted and deformed as the body contracts, increasing the strength of its surface gravity. Assume that a body with a Schwarzschild radius of Rs has radius r, light detection. The most deflected light rays are those traveling tangentially to the surface. Once more, we envision a spherical body of fixed mass that is contracting. All rays emitted tangentially to the surface are bent into circular orbits when the contracting body reaches a radius that is 1.5 times the Schwarzschild radius. As contraction continues, the exit cone narrows, allowing only the rays released within to escape. The exit cone fully closes, and no light rays can escape when the body reaches the Schwarzschild radius. To prevent radiation from escaping a black hole, redshift and detection work in tandem. The surface around which light rays can circle a black hole is called the photon. Once more, we examine what occurs at the surface of a contracting spherical body. Still, this time, we picture particles with rest mass being launched horizontally from a specific point on the surface. Generally speaking, we can determine the velocity at which a particle will orbit in a circle. As long as the period p and orbit radius r are measured in the space and time of a distant stationary observer, particles in circular orbits continue to obey Kepler's law, p squared is proportional to r squared, in general relativity. However, when the radius is less than 3 times the Schwarzschild value, circular orbits are impossible, and particles in this region spiral inward and are ensnared by the black hole. Tilting of the light cone. At great distances from a black hole, gravity is weak, and spacetime is roughly the same as the spacetime used in special relativity. However, spacetime is severely warped near a black hole. A distant observer's time and space intervals. From the perspective of the faraway observer's normal space and time, it is more convenient. Consider a particle falling towards a black hole in terms of the space and time of a distant stationary observer. When we say that a black hole has a certain radius, say 3 or 30, we are referring to the space of a distant observer rather than that of a nearby observer. The particle's light cones resemble those of the distant observer at great distances from the black hole. The particle's light cones tilt as it gets closer to the black hole, and its future light tips in that direction. The curvature of space-time causes this tilting of the light. The particle's future light is tilted so far forward when it reaches the Schwarzschild surface that none of the light it emits escapes to the outside world, and all of it falls into the black hole. The particle only sees the world it leaves and not its future, because the past light is tilted so far backwards that it can only receive light from the outside world. The light cones are tilted even more inside the Schwarzschild surface. All of the particle's light travels ahead into the singularity, and the particle is unable to see the singularity into which it is falling. In its immediate vicinity, the space-time of the free-falling particle is flat and identical to that of ordinary special relativity. As a result, the particle enters the black hole without experiencing any adverse effects. It takes the Schwarzschild radius divided by the speed of light to reach the singularity in its own time. However, it appears to the far-off observer that the particle takes an infinite amount of time to enter the black hole. The survey of points and circles. We can better comprehend the impact of space-time curvature by using emitting points and wavefront circles. We consider a point in space that is stationary concerning the black hole to emit a short burst of radiation. A moment later, the wavefront circle indicates the location of the radiation rays. Space is of the wavefront circle, far from the black hole. The emitting point is displaced away from the black hole and off-center close to it. The wavefront circle is shifted by curved space. In other words, light rays are pulled towards areas of greater gravity by gravity. The dynamic space. If space itself flows into the black hole and takes the light rays with it, this dragging effect would be identical. This dynamic space, which is crucial to general relativity and has significant implications for cosmology, will be discussed later in the context of the expanding space paradigm. While general relativity concurs with special relativity that nothing travels through space faster than light, it also asserts that space is dynamic and that the laws of special relativity do not govern its motion. Space moves more rapidly than light in some places, such as outside the Hubble sphere and inside black holes. As one might anticipate, since space is flowing inward at the speed of light, the emitting point at the Schwarzschild surface is situated on the wavefront circle itself. Rays of light traveling outward at the Schwarzschild surface remain in the exact location. They travel through space that is falling in at the speed of light and move at the same speed. The Red Queen's homeland is the black hole's surface, where one must travel as quickly as possible to stay in one place. The horizon of the event. The event horizon is the area on a black hole's surface where space falls inward at the speed of light. Because light signals cannot travel faster than the speed of light, which is a signal of the event horizon, observers outside the horizon are unable to observe or communicate with events inside the horizon. Signals traveling outward at the speed of light are dragged inward and are unable to reach the horizon because space flows inward faster than light inside the horizon. In the frame of the free-falling particle, special relativity is still applicable locally, and the local speed of light is the same as the one used by the distant observer in free-falling space. The flow of space carries along free-falling observers who employ special relativity locally. A spaceship that plunges into a black hole will always perish because, despite the power of its rocket engines, it will never be able to travel faster than light in its own local space, which is falling faster than light. Perfect symmetry. Black holes that do not rotate are perfectly spherical. This poses a fascinating query. Does this imply that the final black hole is not precisely spherical if the collapsing body is not? Number all. Non-spherical irregularities radiate during the final moments of collapse. A perfectly spherical black hole remains after the gravitational and electromagnetic waves are released into the outside world. The charming expression, "black holes have no hair," refers to this. Gravitational and electric fields are examples of long-range fields of force that persist even during collapse. However, magnetic fields and other non-radial short-range fields of force are either radiated away or pulled in. It has been questioned how gravity can extend past a black hole if nothing can escape. Imagine gravity as radial lines of force. The collapsing body slides down the lines of force, allowing it to survive in the outside world. This is one approach to consider. Understanding that gravity is composed of curved space-time, which is continuous and has no edge, is an additional and superior method. A black hole is still connected to and a part of our universe. It is not a separate universe in itself. Rotting holes in black. Black holes have only been thought to have mass up until now. More generally, a black hole is determined by three fundamental factors: electric charge, rotation, or more accurately, angular momentum, and mass. Only these characteristics remain when a collapsing body turns into a black hole. Since most massive bodies tend to be electrically neutral and are readily neutralized by electrically charged particles in the interstellar medium, significant concentrations of electric charge are uncommon in astronomy. Therefore, we won't investigate how electric charge affects black holes. However, rotation is unavoidable and standard in astronomy. The vast majority of the universe's matter demonstrates significant scale bulk rotation. In general, stars rotate, and their rotation speed increases with contraction. Centrifugal force would cause the majority of stars to split apart long before they had shrunk to the size of a black hole. Nevertheless, dying stars use a variety of tactics to offset the fast rotation of their contracting cores. The spinning core is also halted by magnetic fields and viscous forces that connect it to the slower rotating mantle, and the neutrinos that emanate from the core take away some of its rotation, angular momentum. The core eventually turns into a neutron star, or even a black hole, after losing its fast rotation through a variety of processes. There is no question that black holes and neutron stars typically have fast rotations from birth. Some may even spin at 10,000 revolutions per second at first. It is impossible for gas scattered between stars to fall straight into a black hole from great distances, because it is usually in a swirling motion. Instead, gas will build up and rotate in the shape of a disk cloud around a black hole. Similar to Saturn's rings, centrifugal force supports such a rotating cloud, known as an accretion disk, against gravity. According to Kepler's third law, the disk's inner regions orbit the black hole faster than its outer regions. The disk's inner areas are broken by friction, while the outer areas are accelerated. Consequently, matter in the disk's inner regions loses its ability to rotate and gradually spirals inward until the black hole accretes it. In the meantime, excess angular momentum is carried into space by matter in the outer regions as it rotates and slowly spirals outward. Gas that falls in from great distances continuously replenishes the accretion disk. A black hole would quickly gain rotation from the accretion of swirling gas, even if it didn't have any at first. In areas with high gas concentrations, like close binary systems and galaxy nuclei, accretion disks are formed. The Kerr metric. The Einstein equation for the exterior spacetime of a non-rotating black hole was solved by Carl Schwarzschild in 1916. Roy Kerr solved the Einstein equation for the exterior spacetime of a rotating black hole in 1963, the year quasars were discovered. The Schwarzschild spacetime is simpler than the Kerr spacetime, or Kerr metric. We observed in the discussion of non-rotating black holes that the future light cone tilts towards the black hole due to spacetime curvature. We now have the added effect of future light tilting in the direction of rotation due to spacetime curvature in the vicinity of a rotating black hole. At the Schwarzschild radius, where space flows inward at the speed of light, we have previously envisioned space flowing into a non-rotating black hole, forming an event horizon. Now we have to imagine that space flows around a rotating black hole like a whirlpool. As the particles fall inward, they are carried around by the whirlpool. Emitting points and wavefront circles at great distances from a rotating black hole, as well as the space of the wavefront circle, make it easier to visualize what occurs. As a result of the point's rays being dragged inward and around, close to the black hole, the wavefront circle is partially displaced inward and partially in the direction of rotation. Two distinct surfaces are formed around the black hole in this scenario. Space flows at the speed of light on the first surface, which is referred to as the static limit surface, or simply the static surface. The static emitting points are located at the periphery of their wavefront circles at this surface. The second surface is the event horizon, where space flows at the speed of light in an inward radial direction. Every emitting point and its wavefront circle touches the horizon at this surface. The outer static surface has an equatorial radius equal to the Schwarzschild radius and is shaped like an oblate, flattened spheroid. A particle that is motionless in this flow of space is pulled along at the speed of light about the distant observer. It is the surface where space flows at the speed of light. The term static surface refers to a surface where a particle remains motionless if it moves against the speed of light. Some light rays can still escape to infinity because the wavefront circle extends beyond the static circle. No matter how quickly a particle moves against the flow, it is always dragged along and can never be stationary about the distant observer because space flows faster than light inside the static surface. The event horizon, the inner surface, has a spherical form. Space travels inward across this surface with a radial component of velocity equal to the speed of light. No matter which way they travel, light rays are unable to escape the outside world. At the poles, the event horizon and the static surface intersect. Both surfaces combine to form the Schwarzschild spherical configuration in a non-rotating black hole. The event horizon has a radius half the Schwarzschild value at maximum rotation and decreases to a smaller radius as rotation increases. It rotates at the speed of light about the far observer when it is at its maximum rotation on the event horizon's equator. The ergosphere. The ergosphere is the region between the event horizon and the static surface, comprising swirling space that spirals inward toward the horizon. Though the inward radial component of the flow velocity is less than the speed of light, space in the ergosphere flows faster than light. Some rays can still travel outward and escape to the outside world, but static points are located outside their wavefront circles. It was demonstrated by Roger Penrose of Birkbeck College in London that it is theoretically possible to extract energy from a black hole in its ergosphere. A body is launched into the ergosphere, where it splits into two parts. One part propels itself forward with more energy, while the other part is thrown backwards against the rotation. With energy derived from the black hole's rotational energy, the first component plunges into the event horizon, while the second component escapes across the static surface. The black hole's rotational energy alone accounts for a portion of its mass. Naked singularities are ordinary in black holes, but the energy eruption from these singularities may be so massive that life is impossible in these charred universes. We are here because there are no naked singularities, and the cosmic censorship theory is consistent with the anthropic principle. A black hole grows by accretion to Brobdingnagian size after it is born, and the rotational energy helps it grow by 0.29 of its mass, which is the most mass that the Penrose method can extract as energy. The energy extraction idea discussed here, as well as all the other ideas in this book, is, at least at present, of interest for understanding nature rather than for possible practical technological advances. Warns Robert Wald in Space, Time, etc. The event horizon's radius is half the Schwarzschild value at maximum rotation. Space falls inward at the speed of light, and its surface at the equator rotates at the speed of light. Imagine that the rotation could be increased even more, and the horizon would disappear. In actuality, the inward velocity of flowing space would fall and be less than the velocity of light, while the rotational velocity would rise. After that, radiation would leak out, exposing the singularity to the outside world. The idea of naked singularities has been dismissed by Penrose's cosmic censorship hypothesis due to their concerning nature. According to cosmic censorship, natural laws work together to prevent the formation of naked singularities, and event horizons conceal all singularities from view. Universes are made of matter and eventually die. The potential is enormous in the cores of giant galaxies, where gas clouds and stars are abundant. Tidally disrupted stars' gaseous debris is drawn in by black holes, which can even engulf one another. They expand into holes that are thousands, millions, and possibly even billions of solar masses in size. Energy is radiated by the heated and compressed gas that is pulled in towards the black hole. Up to 40% of the mass of the accreted gas may be radiated. Compared to nuclear reactions, which convert mass into energy at a rate of 1%, this conversion is substantially more efficient. Infrared radiation from nearby dust clouds may also be included in the wide range of optical, ultraviolet, and X-ray radiation that is released. In the matter-rich nuclei of giant galaxies, supermassive black holes with masses of hundreds of millions of solar masses can form over hundreds of millions of years and release energy at an incredible rate. An accreting superhole can emit more energy than a whole galaxy of bright stars. According to the Best Buy theory, quasars are accreting supermassive black holes, and the energy released from these black holes may power powerful radio sources. When a black hole's tidal forces exceed the gravitational forces holding a body together, such as a planet or a star, the body will be torn apart. As a general rule, if the average density of a body held together by gravity is lower than that of the black hole, it will be tidally disrupted. Since a black hole's density is inversely proportional to the square of its mass, its size is proportional to its mass. The compressed gas radiates energy efficiently as it drains inward. However, the energy output decreases as the mass increases to the point where stars are no longer disrupted by tidal forces and are engulfed by the black hole. Stars that approach black holes larger than 108 solar masses plunge straight in. It would be possible for a spaceship to plunge into a million solar mass supermassive black hole without the tidal forces causing severe discomfort to its human occupants. Inhabitants may initially be unaware that they have crossed the event horizon in the case of a supermassive black hole, which has a far greater mass. It is unlikely that Lilliputian black holes of lesser mass will ever be created by gravitational collapse, because all of the black holes that have been discussed thus far have masses larger than the Sun. For instance, a planet like Earth can never collapse and turn into a black hole, because the gravity of these smaller bodies is insufficient to counteract the pressure gradient forces that matter exerts. However, it's possible that the early universe produced black holes with a variety of masses. Cosmologists had speculated that black holes might have formed when their densities were similar to the universe's density, which was very high in the early stages of expansion. Numerous theories involving black holes have surfaced. The time-reversed black hole is one theory. A white hole, in which everything bursts out in a massive release of energy, has been proposed as the result of reversing a collapsing black hole. In astronomical circles, this theory gained increasing popularity in the 1970s. When matter enters a singularity, what happens? One explanation, according to some, is that it appears as a white hole somewhere else in the universe, possibly even in a different universe. In other universes, black holes with equal rights suddenly appear as white hole eruptions in our own. One audacious hypothesis was that matter is siphoned back into the Big Bang, which is hot because it resurfaces as white holes from black holes. The idea of white holes no longer seems plausible, and there is no proof that matter can be moved in this way. Another idea is that black holes create bridges between widely separated areas of space-time. Technologically advanced civilizations are said to have employed such bridges, also known as wormholes, as a means of transportation for time and space travel that is faster than the speed of light. In recent years, the concept of bridges as time machines has gained popularity, especially in the entertainment sector. A time traveler travels almost instantly to a space station at distance L that moves away at velocity v. If the space station is approaching at velocity v, the time traveler arrives at 55 units of time in the future. If not, the time traveler returns almost instantly via a second bridge and returns to Earth in the past at 55 units of time before departure. A source of exotic matter with positive density and negative pressure is required to construct bridges that are suitable for transportation and remain open. Another hypothesis is that offspring universes are born in black holes. The cosmogenic foam that was present in the very early universe is likely similar to the singularities of black holes. According to the theory, every black hole collapses into a singularity, which subsequently expands to create a new or progeny universe. The offspring universe's black holes create more universes, which in turn creates still more universes, and so on. To explain why the constants of nature, the gravitational constant g, the speed of light c, the Planck constant h, the electric charge of the electron, and the subatomic masses, have their finely tuned values, Lee Smolin of Syracuse University suggested that this reproduction of universes serves as the foundation for a natural selection theory. According to the anthropic principle, the constants must be precisely calibrated to be consistent with our existence. According to Smolin's natural selection theory, the constants are precisely calibrated because stars are implied to exist by black holes, which in turn suggest the existence of planets and eventually life and humans. Stephen Hawking, then at the University of Cambridge, proved that black holes release heat radiation in 1974. This astounding finding showed that black holes are not as black as previously thought. We must study the nature of space to comprehend why black holes radiate. Contrary to popular belief, the Hoover is not empty. It is a vast ocean of virtual particles of all kinds, each of which only exists for a brief instant. The uncertainty principle states that although energy can be borrowed, it must always be repaid within a certain amount of time. The faster the loan must be paid back, the larger the amount borrowed. The energy required To produce two electrons, one positive and one negative, for instance, can be borrowed for 10 to the power of negative 21 seconds, and the repayment period for two nucleons is 10 to the power of negative 24 seconds. Virtual particles that constantly appear on borrowed energy and then vanish when the payment is due are present throughout the entire universe. When taken as a whole, they explain a large number of observed atomic structure effects, but none of them last long enough to generate a gravitational field. Subatomic particles are not merely energy packets. They have conserved quantities that cannot be destroyed or changed, like spin and electric charge. As a result, virtual particles are always accompanied by their opposites. A virtual positron, the antiparticle of the electron, has a positive charge and is paired with a virtual electron, which has a negative charge. In one direction, a particle spins, while its antiparticle spins in the opposite direction. The combined spin of these two particles is zero. Virtual electron pairs, or electrons and positrons, with a combined spin and electric charge of zero, are widely distributed throughout the vacuum. Despite having the same mass, particles and antiparticles always possess the opposite values of specific conserved quantities. Therefore, only the joint energy of a particle and its antiparticle have been borrowed when they appear Brisai in a virtual state. Their antiparticles are photons, which are quantized radiation particles. A photon's antiparticle is another photon with the opposite spin. Non-rotating luminous bodies emit both types equally and in equal quantities. Photons from glowing matter, or antimatter bodies, are similar in nature. In addition to all other virtual particles, virtual photons also cause the vacuum to seethe. A virtual particle and its antiparticle do not revert to the vacuum state's limbo whenever they can accumulate enough energy to become real. The necessary energy can be obtained in various ways. We talk about two approaches. Imagine two parallel conducting plates separated by an electric field. The strength of the electric field between the hordes of virtual particle pairs, including electron pairs, which only exist for a short time, increases as the potential difference between the two plates increases. The positron is drawn to the negative plate and the electron to the positive plate during the brief existence of a virtual electron pair. They rarely separate during their short existence because the electric field is too weak. However, the oppositely charged electron and positron separate far enough to receive the necessary energy from the electric field to become real when the electric field is strong, approaching 10 to the power of 16 volts per centimeter. Now, a flood of electrons, positrons, and photons is produced as the vacuum comes to life. Stronger fields produce heavy particles, fields of gravity. Now think about virtual particles in a field of gravity. Although particle pairs accelerate in the same direction, the tidal force caused by gravity tends to split the pairs apart. Black holes produce strong tidal forces, and the smaller the black hole's mass, and thus size, the stronger the tidal force. A virtual particle and its antiparticle are drawn apart to a sufficient distance when the tidal force close to the surface is strong enough, gaining the energy needed to become real. No energy is lost from the black hole, and the majority of the fundamental particles produced in this manner fall inward. However, some virtual pairs split up sufficiently that one of the members can move outward with enough energy to escape. The exact process is used to create photons from the vacuum state. Consequently, black holes continuously lose energy and release particles such as photons and neutrinos in a quantum mechanical manner. Particles break through seemingly insurmountable barriers because of their wave-like nature. This behavior provides an alternative perspective on black hole particle emission. A particle may emerge as a wave after tunneling through the event horizon. The emerging particle's wavelength is most likely to be comparable to the radius of the black hole, Hawking found that particle and photon emission is thermal, like that of a hot body. The temperature of solar mass black holes is very low. There is a temperature difference of only 0.01 Kelvin. The temperature of a black hole the size of a dust particle, with a radius of 10 to the power of -3 centimeters, and 0.1 lunar masses, is 10 Kelvin. Atomic-sized mini-holes radiate intensely and have temperatures of 1 million degrees. Hawking's discovery has shown that, at small sizes, black holes are not entirely black but rather emit radiation. They gradually lose mass and emit energy. Black holes radiate more energy and get hotter as their mass decreases. A mini black hole's temperature and luminosity increase as its mass decreases, and in its last moments, it bursts into a burst of high-energy particles. These mini-hole outbursts might be discovered by astronomers in the future. Heat engines are analogous to black holes. A black hole only possesses electric charge, mass, and angular momentum. These three characteristics are impacted when a body falls into a black hole. Any additional properties are permanently lost. A great deal of data is lost every time a body falls into a black hole and can never be recovered. Matter or antimatter, smaller black holes, radiation or gravitational waves could all contribute to the formation of a black hole, gradually as photons. In addition, the black hole continuously releases an equal number of particles and antiparticles, including neutrinos and other particles like electrons and positrons. Its emission doesn't reveal the origin of the black hole. Even in its last eruption, it continues to release an equal amount of particles and antiparticles as it gradually evaporates. Additional photons may be produced as a result of the released particles and antiparticles annihilating one another. In summary, a black hole is a device that transforms all types of mass into radiation. It is incapable of distinguishing whether the mass was initially composed of matter or antimatter. It disregards the conservation of elements, such as lepton number, except for mass, angular momentum, and electric charge. According to the laws of thermodynamics, black holes are heat engines. They have entropy because they have temperature. Information loss and thermal disorder are both measured by entropy. Entropy either stays the same or rises in a closed, isolated system, but it never falls. By considering energy in all its forms, which constantly descends into less accessible and useful states, we can attempt to comprehend entropy. Entropy increases in the process. For instance, it provides us with high-entropy photons that are devoid of order and information, but the energy that gave rise to them, such as that found in flowers, crystals, books, and planets, has disappeared. The surface area of a black hole's event horizon determines the amount of information it loses. This is comparable to a burning candle for a non-rotating black hole, where the energy is transformed into heat, radiation, and molecules in lower energy states, thereby increasing entropy. When two black holes collide and merge, they create a single black hole with a surface area larger than the total of the two original black holes' horizon areas. However, we know that a black hole radiates its mass and is hot. Its surface area decreases as its mass decreases, which lowers its entropy. The laws of black hole thermodynamics are not broken. Because the emitted radiation carries entropy into space, the black hole's entropy decreases. The black hole alone is not the only closed system where entropy is either constant or rises. However, according to a new branch of physics known as black hole thermodynamics, the total entropy of the black hole, including the entropy of the radiation it emits, remains constant throughout the universe. According to some astronomers, there are billions of black holes in the galaxy. The particles of our bodies, along with the debris of the solar system, will be swallowed by a black hole when it eventually approaches us. Once engulfed, the particles will exist for a fraction of a second before being drawn into the black hole singularity, rather than persisting until the end of the universe. But let's say that the universe eventually collapses and comes to an end. Then, the universal singularity is where all the particles in the universe, including those that have already fallen into black holes, will eventually converge. An easy way to get to the end of the universe is through a black hole. The scientist Arthur Schuster originally used the term antimatter in a letter to Nature titled Potential Matter, a Holiday Dream, in 1898. He conjectured about the existence of antistars and talked about the potential characteristics of antimatter. He wrote, "May antimatter be commended to its care. Astronomy, the oldest and yet most young of the sciences, may still have some surprises in store. Several subatomic particles and their antiparticles have been discovered with high-energy accelerators. Particles and antiparticles are distinguished by their conserved intrinsic properties, such as electric charge and baryon and lepton numbers. For instance, nucleons, protons and neutrons, are heavy particles. Their name comes from the Greek bari, meaning heavy. Paul Dirac developed a relativistic equation in quantum theory in 1930 that revealed the possibility of anti-electrons. 2 years later, the positron was discovered, and in 1955, the antiproton was discovered. The universe is made up of matter because, in the very early expanding universe, the dominant hyperweak force made a very slight distinction between matter and antimatter in their particle decay schemes. Grand unified theories have shown that antimatter is rare in the universe. Antistars in anti-galaxies emit the same. Most galaxies have unmistakable signs of their violent interactions. There are indications of violence, it is true, but not of the kind